Welcome to lesson 5, okay, capacitance. Now you've just watched a video on capacitance, a really good YouTube video on capacitance. If you haven't watched it, watch it now because I'm assuming you have it watched, and we want to talk about capacitance here, right? Now remember, any metal body or any body, we call it a body, any body, we like bodies in physics, okay, any body has a capacitance, okay, so any metal body. So we take this item, okay, quiz question for today. This is a kitchen item. What is it for? Okay, so this item, okay, is a metal body that has capacitance. So I can charge that and has a capacitance. However, it doesn't have a large capacitance for its size. If we want to make a device that has a large capacitance or has a certain capacitance, we call it a capacitor. So everything has a capacitance. Capacitors are components that are made to have a special or usually larger capacitance. In the same way as we'll do it later, we have a resistors. Everything has resistance. Resistors have a certain resistance or a very large resistance or a very precise resistance and so on. Okay, so that's the idea, right? Now our capacitors, right, are the capacitors we're going to deal with are parallel plate capacitors, all of them. Okay, now this may seem odd. Okay, I'm going to get this out of the way first of all, because like that's your example of a capacitor. Okay, that's an example of a capacitor, right? And it seems cylindrical. Okay, but in effect, it's still a parallel plate capacitor. And you'll see this with the rather strange dimensions of the plates in capacitors when you're doing questions. Okay, in that what we have effectively is you've two conductors. So we're taking the 2 pages here to pick 2 conductors, and in between you have an insulator. Now it could be air, but usually it's not air. It's usually some other material. So look, I basically, okay, that's a conductor, so like aluminium foil. That's an insulator, some kind of plastic, and that's a conductor. So there you go. That's your parallel plate capacitor that we'll be talking about. Okay, its dimensions, length by width, and so on. Okay, but what you actually do in real life is you roll it up. Okay, so you roll it up. Okay, I haven't rolled it up very well, but you roll it up like this. Okay, so effectively it's still a parallel plate capacitor. Okay, but it's now cylindrical. Okay, and voila. Okay, so that's why you'll see areas of capacitors having a very small width, let's say 2 centimeter width, and it could have a length of 5 meters. Okay, because it's loaded, wrapped up like that. Okay, so that's a parallel plate capacitor, believe it or not. Okay, now our definition of capacitance, and we've looked at that in very good detail in the video, is Q over V. Now you can't change the capacitance of a capacitor. Okay, because if you put on more charge on the plates, the potential difference across the plates gets larger. If you put 4 times more charge on the plates, the potential difference gets 4 times larger, so the capacitance stays the same. Okay, so that's a kind of a property of the material, right? Capacitance. Okay, and from that we can define the farad. Okay, and we look at our definitions. Okay, the farad, 1 farad, okay, is effectively 1 coulomb over 1 volt. Okay, so when there's a charge of 1 coulomb on each plate for a potential difference of 1 volt across the plates, right? That's capacitance. Okay, and we look at calculations of on these as we go along. Okay, the second thing we need to look at is the idea of energy stored in a capacitor, and we have an experiment to follow. Okay, and the formula is half CV squared. Now we don't have to derive this. Okay, we will look at it next year. We don't have to derive it. Okay, but it actually comes from just our definition of voltage and this effectively put together. Okay, we'll come back to it. It's not a derivation. All we have to be able to do is use this formula. Okay, half CV squared. Okay, obviously if you don't know C, you're going to use Q over V. There's 3 formulas here that are going to come together, and we'll be doing calculations in a minute in your assignment 2. Okay, or there too. Okay, right, this is your formula. So remember the idea of that. Okay, I've done an example, but it wasn't very it wasn't much of a flash on the bulb. So what I've done here is I've prepared one earlier. Okay, so this is a capacitor. Okay, so it's a 470 microfarad capacitor, so half a millifarad. Okay, I've charged it with a power supply, and then okay, it's been sitting there. Okay, it's been sitting there, but the charge stays in the capacitor, and we connect up like this, and there you go. That was a good flash. Okay, and that's like your flash in your camera. Okay, that's the flash in the camera. So that's an example. That's the simplest example of the use of a capacitor. There are other uses that we will look at as we go. Okay, third formula that we'll be dealing with is the capacitance of a parallel plate capacitor. Now it should make sense. It's proportional to the area of the plates, but it's the common area of the plates. Okay, it's the common area of the plates. Now what do you mean by common area? At the moment, the common area is the area, okay, but you could move one of the plates, let's say to here, okay, and the common area then is the area of overlap. And there are things called variable capacitors which do this, okay. If you change the area of overlap of the capacitor, you're reducing the capacitance, or if you reduce the area of overlap, you reduce the capacitance. So so the area is the area of one plate, not two plates, and it's the common area, the area of overlap. Okay, so be very clear on that. D is the distance between the plates, which can also, and the closer you bring them, the greater the capacitance, because of the plus and the minuses holding each other. Okay, so the D is capacity. The closer you get, the greater the capacitance, and it's an inverse relationship for capacitance is proportional to 1 over the distance. Okay, and we have a constant, and the constant is the permittivity of a vacuum, okay, or a free space, okay, and it's epsilon 0, and that's the form we've used already, or that's the constant we've used in Coulomb's law already, and electric field strength. So you know, Q1 Q2 over 4 pi epsilon d squared. Now, what's important here is if you're given the relative permittivity, this is the permittivity, it's on page 47. If you're given a relative permittivity of 6, that indicates that the permittivity of the medium in between the plates, which we call the dielectric, is 6 times the free space. So you just multiply it by 6, and we'll have calculations like that. Okay, so just be clear on this. You have 2 plates, you have an insulating material here, it could be air, okay. Now that insulating material is called the dielectric, okay, right, and the dielectric has a permittivity, 2 T's in the middle and 1 at the end, okay, but not that it will be a spelling test, okay, it's the permittivity, okay, right, so this is the permittivity of free space, that's the permittivity, okay, epsilon 0. Now, the relative permittivity, so if we're told the relative permittivity, sorry, got it wrong, is 2. Okay, so then therefore the permittivity is 2 times epsilon 0, which is 8.9 by 10 to the minus 12, and you get your answer. Another name for relative permittivity is the dielectric constant. Okay, but I don't think you'll come across that, but just be aware of the dielectric constant. So the dielectric constant is 4, that means its relative permittivity is 4, so its permittivity is 4 times the base value, which is the permittivity of free space, which is effectively the permittivity of air. Okay, 8.9 by 10 to the minus 12. They're the formula. Okay, it's really an example, a set of questions where you get into capacitance, okay, and you have to be able to just deal with the 3Ds together. Okay, they're your toolkits, stream them together and you drive on. One other thing that, it's fierce important, okay, and I think this is the most important thing and the thing that people miss the most, so since it's so important, we'll clear it up, okay, we'll have no distractions. Okay, this one is a little bit counterintuitive, okay, right. It's incorrect to say that a capacitor stores charge. It's incorrect to say it stores charge. What it does is it redistributes charge. It doesn't store charge, it redistributes charge. So before we charge this capacitor, okay, it's neutral. There's an equal number of plus and minus charges on both sides. We don't usually put that in because we assume that if there's nothing there, it's neutral, okay? When we charge it, let's say plus charge on this side and minus charge on this side, okay? What's happening is we've redistributed the charge. You can think in terms of plus and minus charges, or let's say just think in terms of electrons, which are negative charges. What we've effectively done here is we put more electrons over here, but we've taken them from here. So when we're talking about charging a capacitor, the term is kind of funny. Charging means redistribute the charge to store energy, redistributing to store energy. It's the same as putting books onto the top shelf, as we looked at before, okay? You're redistributing the mass to store energy. You're storing potential energy in the book. Here you're storing potential energy by redistributing charge. So if you move big boulders to the top of the hill, okay, you are storing potential energy in those boulders. Okay, you're doing work to store potential energy. When you're charging a capacitor, you are redistributing the charge, you're doing work, okay, and that work, that energy is stored in the capacitor. So you store energy, but the net charge on any capacitor is 0, okay? When we talk about Q in the calculations, That's the charge on each plate, not the total charge. So what's the net charge on a capacitor? 0. Okay, and that question comes up quite a lot, and people do, as you can imagine, very badly, but you are not going to get caught. Thank you. Bye-bye.